Just prior to the start of our school year, the Ministry of Education released Focusing on the Fundamentals of Math Teacher and Parent Guides. The Teacher Guide is intended to support teachers' efforts to build students' knowledge and skills in mathematics. In this presentation, we will highlight the intent of the document and the impact for Dufferin PO. The Teacher Guide focuses attention on expectations found in the Ontario Mathematics Curriculum Grades 1 to 8, released in 2005. Specifically, it highlights expectations in the number sense enumeration strand and expectations that relate to number properties in the patterning and algebra strand. Fundamental math is categorized into a framework that has 5 components: working with numbers, recognizing and applying understanding of number properties, mastering math facts, developing mental math facts, and developing proficiency with operations. The continuums found in the document highlight number sense enumeration and patterning and algebra expectations from the curriculum and categorize them into the 5 components of fundamental math. These continuums, like the trajectories found in the Nelson pre-assessment and continuums from researchers like Dr. Alex Lawson and Kathy Fosno, show the developmental progression of concepts and skills that can help inform our instructional decisions.
As indicated in our curriculum document, students need to have computational fluency. The guide reminds us that building computational fluency is best achieved using a variety of strategies. As with everything that we do, we always need to begin where students are. Pre-assessments like Nelson and Knowledge Hook can provide us with information about a student's current understanding and possible next steps. The 3 components of computational fluency are accuracy, efficiency, and flexibility. In order to be computationally fluent, all 3 components must be present. Just like in reading, where we ensure that students are not only able to decode, but more importantly can comprehend what is read, computational fluency requires more than just getting to the right answer. We want our students to have efficient and flexible methods supported by number and operational sense. Consider, how would you solve 1000 minus 998? Now, let's consider 2 student examples, which help us see the difference between students who memorized a procedure and students who have computational fluency.
1000 minus 998.
Two.
And how did you figure out the answer?
Well, I did repeated addition. Repeated subtraction. How I did the same thing in the first problem. How I just took out the 1 and made it and put the 1 in front of the 0, and that was a 10. I crossed it off again, and that was a 9. I did the same thing again and again until I kept getting my answer.
Okay, so when you say repeated subtraction, you were kind of thinking the way you would do it with pencil and paper?
Yeah.
With crossing things out?
Yeah.
Okay.
$1,000 minus 998.
2.
That was fast. How did you figure out the answer?
Because 100 minus 98 is 2, so I was just thinking about 998 plus 2 is equal to 1,000.
This is an addition problem. 99 plus 17.
116.
And how'd you figure out the answer?
Because 90 plus 10 is equal to 100, and then 9 plus 7 is equal to 16, and then that equals 116.
Thank you.
What did you notice about the student responses? Both students were accurate. However, was the first student's method efficient? Do you think she has a variety of strategies that she can draw upon? Now think about the second student. Did she look to the numbers before selecting a strategy? Was her thinking more efficient? The second student demonstrates computational fluency.
Reading is foundational to literacy, just as computational fluency is foundational to mathematics. Teaching a child to read requires year-long instruction, which must incorporate all 5 components of reading: fluency, vocabulary,
phonemic awareness, phonics, and comprehension. Likewise, building a child's computational fluency requires year-long instruction and must incorporate all three components of computational fluency: accuracy, efficiency, and flexibility, as demonstrated in the visual.
Have you memorized the answer to 13 times 14? Probably not. What strategy would you use to solve this problem? When you understand a variety of strategies that you can draw upon, you can rely on thinking, grounded in the relationships among facts, to get the correct answer. Exploring a progression of strategies, how they develop over time, is important for students when developing fundamental math concepts and skills. There is a difference between memorization and automaticity. Automaticity relies on thinking about relationships among the facts. The question is not whether we want our students to know their facts. The question is how to get there. The how relies on implementing good pedagogy. Some strategies that support computational fluency are number strings and number talks.
These guides are not a call towards drill and kill. Instead, they call for a personalized program that is balanced, based on assessment, and uses a variety of instructional practices that meets students' strengths and needs. In order for students to master their facts, practice needs to happen. However, what it looks like may be different from what we experienced as students. These days, practice can be in the form of rich tasks, games, and applications like Knowledge Hook.
What is the impact of this for Dufferin PL? You should focus on computational fluency all year long. Use strategies like number strings, number talks, and doc talks to build computational fluency. Focus on mathematical reasoning. Redefine what student practice looks like. Develop content knowledge for teaching by using trajectories, continuums, and landscapes. Value student thinking and how it connects to formal methods like algorithms and procedures. And honor the concrete, representational, and abstract model.
Consider how you would answer this question. There are 125 sheep and 5 dogs in a flock. How old is the shepherd? Yes, to us as adults, this question sounds ridiculous. But let's watch how 32 8th graders attempt to solve this problem.
There are 125 sheep and 5 dogs in a flock. How old is the shepherd?
What? There are 125 sheep and 5 dogs in the flock. How old is a shepherd? I don't know how to solve this.
Why is that?
Because it doesn't talk about anything about the shepherd. Like, it doesn't say how old, like how long he's had them or anything. So it doesn't give me any hints about anything. Yeah.
Okay. Thank you very much. There are 125 sheep and 5 dogs in a flock. How old is the shepherd?
$120 years old.
How do you know it's 120? Can you please write down that? Now, how do you know that the shepherd is 120 years old?
Then we subtracted 125 minus the 5 dogs in a flock.
Okay, thank you very much. Thank you. Can you tell me, how did he know to divide?
Because it doesn't say the difference, or it doesn't say the sum, or the project, or something.
Okay, thank you very much.
This video really highlights the importance of promoting reasoning in mathematics rather than blindly applying skills.
For further details about fundamental math, please refer to Focusing on the Fundamentals of Math, a Teacher's Guide and a Parent's Guide to the Fundamentals of Math, grades 1 to 8.